This binomial expansion. It's so hard. I wish I had something that could help me.
I know! You could use Pascal's Triangle!
Pascal's Triangle? What's that?
Let me show you.
Blaise Pascal was born in Piedmont on June 19, 1623. At first, his education was limited to only the study of languages and was not to include any mathematics. However, when he was 12, he asked his tutor what geometry was out of curiosity. His tutor responded by telling him it was the science of constructing exact figures and of determining the proportions between their different parts. Pascal was hooked.
So let's get into Pascal's triangle. Okay, so to start Pascal's triangle, you start with a 1 and 2 ones underneath it. From there, you just add the two adjacent numbers, and then there you have it. You have Pascal's triangle. Along the edges, as you may notice, there's always a 1. That doesn't really have anything to do with the adding, but that's just how it is. So, the patterns within the triangle. So, I'll just write this out here. Okay. First, we're going to look at the diagonals. So this first one is very obviously just ones. The next diagonal is also pretty easy to recognize, and it's counting numbers. The next one is a little different. It's triangular numbers. So what that means is that for each number, that's the amount of dots it makes to make a triangle. So 1, 1, that's triangle. 1, 2, 3, there you go. 1, 2, 3, 4, 5, 6, and that makes a sort of triangle thing here. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then that makes a nice triangle there. So the next one is then tetrahedral numbers. And that's something completely different. We won't look at that today. Okay, next pattern we're going to look at is odds and evens. So basically what that means is when you write out Pascal's triangle and you highlight the odds and evens, you get this sort of pattern thing. So what you may notice as we're highlighting them is that it kind of goes in like this sort of upside down triangle pattern. And yeah, so here you see that the triangles, and if we went on further, there'd be a bigger triangle there. And what this represents actually is Sierpinski's triangle, which is sort of like a triangle which branches out into more triangles, and then you eventually get this sort of cool triangular shape. So next is horizontal sums. That means that we're going to add the rows, and the sum of that makes a pattern. So that's 1, that's 2, 4, and then that's 8, 16, 32, 64. And as you can see here, the numbers, they're doing something cool, and actually what they're doing is they're doubling. So this could be called horizontal sums, or we could also label it powers of 2. Okay, next pattern we're going to look at is exponents of 11. So if we write out Pascal's triangle like this, what we're going to do is we're just going to put the numbers next to each other. So 1 equals 11 to the power of 0, and then 11, because we're putting the two ones together, equals 11 to the power of 1, and then 121 equals 11 to the power of 2, 1331 is 11 to the power of 3, and so on and so forth. And this actually works until you get to 11 to the power of 5. Then you have to do something a little bit different. So if we write out the numbers here, so 1, 5, 1, 0, 1, 0, 5, 1, what we're going to do is we're going to overlap some of the numbers, because then what we can do is we can make it equal 11 to the power of 5. So if we change these here, what we then have is 1, 6, 1, 0, 5, and 1, and that is equal to 11 to the power of 5. Then that's the same for 11 to the power of 7, and so on and so forth. Okay, now let's take a quick look at how the Pascal's triangle can relate to the Fibonacci sequence. So we'll just write this out. So Fibonacci, basically you start with 2 ones and then you add the 2 numbers behind it. So it looks a little something like that. So we should write out Pascal's triangle now so that I can show you how this relates. Okay, so basically the top one is 1. and 1. And then the next one we highlight 1, so that relates as well. So then we highlight 1, we go up and over 1 and 1, and 1 plus 1 is 2. And then we go 1 up over 1, 1 plus 2 is 3. And then we have 1, 3, and 1, that's 5. And then 1, 4, 3, and that is 8. And this continues on, and it actually works all the way through Pascal's triangle, and it always stays the same to the Fibonacci sequence. So that's 1, 1, 2, 3, and yeah, that's how it works. It's pretty cool, right? Okay, now that we've gone through that, we've actually covered all the patterns of Pascal's triangle. Oh, actually, last one. So, very simply, if you write out Pascal's triangle and we look at the two sides, what does that have?
But Pascal's
Symmetry.
triangle is
Now
very
onto bigger
useful
and
in
better
everyday
things.
life, specifically gambling. Pascal's triangle can show you how many ways heads and tails can combine. This can then show you the odds or probability of any combination. For example, if you toss a coin 3 times, there is only one combination that will give you 3 heads, but there are 3 that will give 2 heads and 1 tail. Also, there are 3 that give 1 head and 2 tails, and 1 for all tails. This is the pattern 1, 3, 3, 1 in Pascal's triangle.
So, now let's look at a new method of finding terms in Pascal's triangle. This method is actually called the n choose k method. It can be written out as n over k, n exclamation mark over k exclamation mark, n minus k exclamation mark. Or a bunch of other different ways really too, but all of them equal the same thing anyways. So, a little side note for you, the exclamation mark you just saw is actually factorial, meaning that if we had 4 exclamation mark, that would be 4 times 3 times 2 times 1. Or if we had 7 exclamation mark, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Or 1 exclamation mark just equals 1. Okay, so let's write out this Pascal's triangle in a term row perspective. So the first number is going to be the row and the second number is the term. So the first row is 0 and then it goes on from 1 and the first term is always 0 as well. So if we write it out that way, it looks a little bit like this. So let's look at row 3, term 2 in Pascal's triangle. So that would be 3 over 2, and then we put it into this, and then we do a little simple math, and we end up getting 3. Okay, now let's take a little look into binomial expansion. So we all know how to do a little procedure called FOIL, which is basically you take a binomial and you learn how to expand it. And so you go outsides, insides, and blah blah blah, and you get a little nifty answer sort of like this. Now that's all good until you have a question like this and you have to expand it using FOIL. There's got to be an easier way. So let's start out by writing out a series of questions using different exponents. We're going to use all variables just to make it easier. Now if you take a look at the coefficients while I'm writing this out, you'll see that that actually has something to do with Pascal's triangle. So as we're writing this out, we're taking some time here, and we'll do this last one here, 1, 4, 6, 4, and last one 1. So let's just write up Pascal's triangle here. So now let's look at the coefficients. The first one, that's 1, and what is that? Row 1 in Pascal's triangle. The next one's 1 and 1, and that's row 2. Then it's 1, 2, and 1. Do we see how this is relating to Pascal's triangle? So that means that if we had x plus y to the power of 5, the coefficients would be 1, 5, 10, 10, and 5 and 1. So now we have that cool thing to figure out the coefficients, but let's look at the variables. So if we look at the variables and we look at the exponents on the variables, you can see that x is decreasing from the exponent on the original question and y is increasing from to the exponent. So that would mean that x plus y to the power of 5 would be this series of variables. There we go. So, in conclusion, we can see that powers of x descend from 5 to 0, and the powers of y ascend from 0 to 5. So all in all, this triangle can be used for so many different things, and we don't nearly have enough time to cover them all in this video. But we just want to say thanks, Pascal. You've really done a lot in the mathematical world.
In 1650, he began to study religion. 3 years later, he went back to his old life and made experiments on the pressure made by gases and liquids, and invented the arithmetical triangle. However, all this hard work did have an effect on his health, as it was affected by his chronic studying. He suffered from insomnia and acute dyspepsia. One night while studying, Pascal collapsed on his desk.
Oh, now I get it. Thanks, Pascal.